Great. Okay, so we're all set up now, and we're gonna get ready to hand it over here to our speaker for today, who is Dick Kroon. And so he's joining us from the UK, Edinburgh, I believe. So it's a bit early for you, which we very much appreciate. Thank you. And so just again, a reminder, please type your questions into the chat, and we can either take them during Dick's talk, maybe, if you would like, Dick, or we can wait until the very end. So with that, we can start sharing your screen and just kind of give it away to you so you can tell us more about what you've been working on.
Oh, hang on. All right, can you all see it?
Almost. There's a large gray bar at the top of your screen.
Oh, that's disappeared.
Ah, there we go. Yes.
Yeah.
Good.
All right. Well, good morning, everyone. And it is literally good morning for me. It's very early, really. But that's okay. It's a lovely, lovely day in Edinburgh. So never mind. And thank you very much for inviting me to give a lecture here and in this seminar series. And I'm delighted with the lecture so far. It has been quite interesting for me. And the reason is, I mean, I started 30 years ago with Leg 117 on working on the Monsoon. Can you imagine? 30 years ago. And in those days, we had very primitive thoughts, and everything was totally different from now. Different proxies, different thinking, and in those days we were thinking very simple uplift of the Himalayas, and the Monsoon would start off, and we thought to drill boreholes and look for orbital cycles in particular. That was what the whole leg was about, and it was all about Kutzbach modeling type of thinking. Uplift of the Himalayas meant basically basically a strong monsoon, southwest monsoon. And but now I've listened to all these lectures, and I've seen over the last decade totally different type of records coming in, and new thinking that perhaps it isn't so simple as that, just the uplifting of the Himalayas influencing monsoon, but there is maybe a bit more to it. And there is global climate change, for instance. And the question is global climate change actually also varying or changing in tandem with the monsoon, or is it even influencing the monsoon, or vice versa? That's also possible. And there is Antarctica, freezing in of Antarctica. We have seen that a lot over the last few days as a potential driving force somehow of the monsoon. So it's all very, very different than 30 years ago. And it was a delight for me to see all this developing. But I still will come back to Leg 117 because there are still interesting records appearing from some of the boreholes, which I would like to show. But before I go to Leg 117, I'm going to the Atlantic. And then you may think, why is he doing that? Well, I'm doing that to show you the main global events in the Miocene from a different ocean basin. And the reason for that is, once we know the ages of these global climate changes in the Miocene, we can maybe better separate out global events from the regional events in the Northern Indian Ocean. So if we find maybe unique Northern Indian Ocean events, we can surely say they must be tied to the monsoon. The global events may be more difficult to interpret. And so that's why I'm going to the Atlantic first. And then we go back to the Northern Indian Ocean. And it was a long time ago that we saw these first compilations of isotopes appearing. This one, Sakos et al. 2001, quite a while ago now, and is now being replaced by the Westerhold one in 2020. I'm showing this because at the time we had a strong group of scientists interested in the Paleogene, and among them was Jim Sagos and myself, Jerry Dickens, and many others, Paul Wilson, Dick Norris, and a group of about 12, 15 people who met in the so-called Extreme Climate PPG of IRP, and that meeting was here in Edinburgh. I organized it myself. And in those days, the Paleogene wasn't seen as important for drilling because we could never drill it completely, recover it completely. We couldn't do orbital tuning because of that, and so on and so on. And we said, no, you can do that. Just go to the right places and drill the Paleogene where it's not so deep. And 4 or 5 legs were born from this group. And one of them was leg 208 that went to the South Atlantic and drilled the Wolfish Ridge. With the particular reason of the Paleogene, but the interesting point about that leg was that we also had a very good Neogene. So I'm going to show you now some of the Neogene results from that particular leg. And that leg was drilled, I think, in 2003. And we had an amazing group of scientists on board, amongst others. Hang on, I need to. Amongst others, Appie Sluis here in the foreground. Here's Appie, here's Isabella Raffi, Dave Odell, Monecki, and many others. Debbie Thomas, I'm seeing sitting here. I'm sitting here at the back as a very young person, as one of the coaches. And these people are paleoceanographers and first-class ones, and we're very much into orbital tuning and discovering global climate events in the South Atlantic. And so I was very lucky to sail with these people. Of course, we shot seismics beforehand, and the sites, actually DSDP, the Deepsea drilling project, already drilled there. And so we knew more or less how deep we had to go in the different basins to reach the Paleogene, and of course, covered by a nice Neogene. So here you see the leg 208 sites together with DSDP sites. And actually, the site I'm going to talk about is 1264, which is rather high up on the ridge. So it's Carbonate ridge and had an excellent Neogene. Now, this leg was designed, as I said, to look at the Paleogene. And we drilled a deep sea transect, as you can see, from shallow all the way to deep in the basin of Angola. So the site I'm talking about is 1264. And we drilled unbelievably beautiful cores, a tremendous cyclicity throughout, all the way from the Neogene down into the Paleogene, all the way to the Cretaceous. So in fact, we can get a full record of the whole Kenozoic at that site. And the good thing about this area is that there is lots of Willistorphi, Cibicidodes Willistorphi present in the sediments, so very good for stable isotopes and so on. So ideal for paleoceanographers and complete. The whole thing is complete here. And so as an example of one of these excellent cores, you can see here the Paleocene Eocene thermal maximum represented by this clay here. Beautiful core. You see some players of leg 208 here. You can see the quality of the cores is enormous, and even today it's even better. So that's important, an important statement to get at the cyclostratigraphy, to get at beautiful cycles undisturbed by coring. And so this leg became really famous because of this PETM here. And the Cretaceous tertiary boundary, as you can see here, this is the Cretaceous tertiary boundary. Now, to show you the difference in quality of drilling in the DSDP times versus the ODP times, I've here on the left, I have here a science paper with the same, from the same area drilled during DSDP. Here is, in fact, here is the Maastrichtian and here is the Paleocene, and here's the iridium layer, and here's the boundary. Now, if you look at this, it's totally broken up and pieces and disturbed and not complete probably in those days. And this is in the 80s. Now, ODP, like 203, drilled this type of core, recovered these type of cores, beautifully, completely recovered with a very nice boundary, although we see a bit of smearing along the liner and some bioturbation. This borehole here is the recovery of the boundary is even better. So Paleocene, Cretaceous. So the entire record is there and with beautifully cored material. To give you an example of the Paleogene, and then you think, why is he doing that? Well, this is the Monsoon. This is the Paleogene here from 52 million to 67 million years. And what you see here is two sites plotted together, one in the Atlantic and one in the Pacific. That's the purple one. This is the carbon, the very general shape, as everybody knows, in the Paleogene. And here is the delta 18O. We see the warming of the ocean here beautifully. We see in the carbon the PETM here. But what we discovered during the lag was that there wasn't just one carbon isotope excursion in tandem with lightening of the delta 18O, so that's warming of the deep ocean. There were many more, as you can see here. You can see here very many more carbon excursions in tandem with the delta 18O. Now, this is very typical for the Paleogene, and particularly for the Eocene. And the interesting point about that is that this is most likely a monsoonal world, as explained by Westerholt et al. No ice in the world, and the monsoon was more dominant. And these events are only present very much in the late Paleocene, Eocene. As you can see, there are some others earlier on in the Danian, like this late Danian event, and some others along the line. Typical of a monsoonal world, so we cannot say that the monsoon is very unique in the Neogene. It isn't actually. The monsoon was always there, of course, but it's just a different type of monsoon system in the Neogene. And so let's go now to the Westerholt et al. Paper. You can see the difference with the 2001 Jim Sackers et al. Paper. In the Paleocene, Eocene, Jim Sackers, his compilation didn't have much structure in this early Eocene. And you can see here now with the new drilling of Orpheus Ridge, and that there is much more structure in this whole system. And you can see beautifully the carbon isotope excursions driven by PETM, very beautiful. And that's the monsoon world. But now we go to the Miocene here. And what we see here in the Miocene here is this Monterey excursion in the carbon isotope. It's a period of organic carbon burial. And the world was actually quite warm in this Miocene climate optimum. Before that, we have the Oligocene-Miocene transition. Still a very warm world, really. And we don't know very much about that. It's just, but that is just driven by 100K cycles, bundled by the 400K cycles. And of course, these cycles were driven by Antarctica changes regarding the ice volume over there. So interestingly, during the Miocene climate optimum, Antarctica was almost ice-free, which is quite a statement, really. Very warm world. And then we plunge into this cooler Miocene world, late Miocene. And here we have the middle Miocene climate transition. And you see here an arrow, which is about 14 million years. And that's deliberate here. That's the big transition when the world started to freeze in again. And then, of course, we have the late Miocene with some cooling here clearly, and then very nicely we go into the Pliocene Pleistocene with the regular ice ages. Now, if we see this record here, then you may wonder what is global here and what is not, and what can we find in the Indian Ocean and elsewhere. So the 40 million year is obviously very important. But then if you look here, then you don't see that much change in the ice volume in the Miocene, except for a bit of change here around 9 million years, sort of cooling down. So let's look at some at site 1264. And we're going to use the carbonate content record to see when the world changed. And that's probably around 14, but maybe there are some other events here that are coming through. So we are using the XRF system to estimate the carbonate content of the sediments, as you can see here. Here's carbonate content, and here is the XRF. Here are the XRF results. The logarithm of calcium over iron seems to work best. And so by pulling the course through the XRF system, we can then have the carbonate content all the way down to 300 meters through the Miocene for the last 30 million. This is 30 million years, in fact. And so it's a near continuous record. We had to fill the gaps here with two sections from another site 1265. Now, I have to say here, Anna Drury is really the driver of this, together with the normal culprits who work in the Neogene and who are mainly paleoceanographers and cyclostratigraphers. So Anne kindly provided me with these slides. And as you can see, the carbonate content doesn't vary very much, but still enough to see the cycles and trends through the last 30 million years. And you can see the carbonate is high here and is lowest here. Also, you can see the amplitude of change, which is quite important. By the way, you can also see the core here. The whitish colors are the most carbonate-rich sediments, and of course, the darker ones are the less carbonate-rich sediments. Now, the carbonate record, which is here in red, had to be tuned to insolation, which is the black curve at the top. There were two parts of the record where we have stable isotopes. That's in the last 5 million years. These were done in Edinburgh. And here we have 18 million years to 30 million years, which is published in the Lebrant et al. Paper in PNAS. The interesting point about this is that tuning is quite difficult because the dominant beat of the system is not constant. And that's seen in many basins, all over, in many boreholes all over the world, but you see it particularly well here. And here we tuned the carbonate minima to the insolation maxima, and in the top of the record, vice versa. And the reason for that is you can check that with the isotopes. And so somewhere in between, there must have been a switch over. Now, when we plot here the full record in time, that's of course after tuning. And then once you have tuned it, you can see we have the sedimentation rates. And you can see there's really low sedimentation rates around here and very high sedimentation rates since about 7.5 million years or so, and then slowly dipping down. These are important observations that I will come back to. So, next one. So what did we do, or what did Anne do, and colleagues? Anne has done all this. That we have the carbonate, as you can see here in the red colors, and we have the insulation record, and we can nicely put them together on top. And we have the isotopes in this part of the record. This is a window from this interval, and you can see how it has been tuned in this interval, basically all the way down to 8 million years, basically based on eccentricity cycles. Although in some places of that record, the tuners used actually tilt, and that was in the places where the eccentricity was weak. So that makes all sense. And so we got beautiful correlations. For instance, here in the top of the record, as you can see, we have the isotopes, and you can see how the carbonate nicely links in with the isotopes. And in this case, also with LRO4, the record that everybody is using for the last 5 million years or so. And then here you see it vice versa in the earlier, from 4.6 to 6 million year. And we can see now that the carbonate maxima are tuned to the insulation maxima. So now we have the full record here in time, beautifully tuned, and the switch over basically was at around 7.5, 8 million years from eccentricity cycle to 40K cycles. But that's something to remember, 8 million years. And here we have the full record now, and here we have the carbonate content record, and now we can calculate mass accumulation rates. And here you see really very nicely how the carbonate productivity changed through time, with since 7.5 million years, these high carbonate productivity in the late Miocene. Now that is important, that 8 million years, because that's coming back in the Indian Ocean. And the question is, what does it all mean? So what do we have? We have an eccentricity-driven world with very, very strong precession in the last bit of the eccentricity world, and then we go to the obliquity world at 8 million years. It's not to say that obliquity isn't here in this world, it's just less strong. And it's actually quite something special from the last 8 million years that obliquity becomes so strong. So we have the lowest carbonate sedimentation rates around 18.5 to about 14. You can see it beautifully in the core here, actually. Now that's important. That's the carbonate crash here. You can see it ramping up towards that 8 million. And the question is, how does this relate to the entire system? So 40 million years and 8 million years are two events that are extremely important in the global climate system, when the whole system changed from one system to the other. And so if we look at the classic definition of the middle Miocene optimum, let's say from 17 to 14, here's 14. So 14 is the most important date. Then we can see that the low sedimentation rates actually started earlier, somewhere around 18.5 million years, ending at 14. So we have a very warm world here. Actually, in the earliest Miocene, it was late early Miocene, it was already very warm. And of course, that's a high CO2 world. And we have probably dissolution going on in the deep sea. And it predates actually this optimum in the Atlantic. So then we have the cooling. And then you can see here in the wavelet analysis, you can see the precession coming in from 10 to about 14 million years or so. So that's that bit where the precession starts to dominate, and the whole system responds very, very closely to precession. If you say precession, you think immediately monsoon, by the way. So the precession is here totally lacking in this very warm world. It has the lowest sedimentation rate. There will be some precession because it's simply difficult to spot when the sedimentation rates are so low, and it depends on your sample density and so on. Now, if you then look at this system, we have an eccentricity system taken over by a precession system modulated by eccentricity, I presume, and it happens in between 13 and 14 million years. So again, 14 million years, that's the timing of global change. Now, what's happening there then in the South Atlantic is very difficult to say. Most likely, we have a total reorganization of surface or deep water in the Southeast Atlantic. And if that's the case in the Atlantic, why not in the Indian Ocean? So what it precisely means is actually not really clear. And we all, I think, have to work hard to understand what's going on there. So if we replot it then, we see obliquity taking over at 8. So that's the next very important date. So 14 million years and 8 million years. And the question is, do we see that in the Indian Ocean somehow? And perhaps there are other events in the Indian Ocean that don't relate to these two age levels. Now, if we now look here in this carbonate increase here at 8 million, that is basically an expression of the late Miocene biogenic bloom. Everybody has been talking about that over the last decades. When we drilled 117, we had no idea about all these things. Just uplift of the Himalayas, upwelling cells, and that was it. And so here we start to see that some of these events, like increase in carbonate production, were actually global. It's not just in the Atlantic that we see this. We see this actually also in the Pacific. As you can see here, this is the Atlantic record in the top, and here at the bottom we see here a whole series of carbonate records from the Pacific, and that's very interesting. We see here the same increase in carbonate production. Again, carbonate blooms in the Pacific. So it's most likely we will see that in the Indian Ocean as well. But can we then still call it monsoonal or not? That's the question. Or is it just globally driven? So now I'm going back to Leg 117. This is 30 years ago. This is myself in the Arabian Sea during Leg 117. And I brought my plankton nets. And everybody was delighted on board, even the captain. And he said, "Oh, just take a dinghy or take the Zodiac and go out and go fishing." And I did. I think that the mate helped me. And so the two of us, and also Caterina Negrini, the radiolarian specialist, went with me. And so we went out fishing in the Arabian Sea. And look how flat the sea was. It was just amazing. Must have been in between monsoonal winds somehow. Anyway, I was fishing there, and of course, I found my beloides, my beloved beloides. And I want to talk now about these beloides curves. So here is Leg 117, and we drilled offshore Oman here, a number of sites and several sites on the ridge here, and Warren Prellen was co-chief scientist, and all together with Nobu Niyazima, and we had a lovely time on board, and I've never learned so much as during that leg. I was one of the biostratigraphers trying to date the sediment, and I did that for the first time during that leg, so it was quite something, but we managed to do it. And here on these ridges, you see the site 722 and 731, and then we have a series of sites along the margin. Of course, then here are the upwelling cells along the margin, and it's all about this Findlater jet, a jet system that drives the upwelling during the southwestern monsoon, and we have low pressure above the Tibetan plateau. That was the whole idea. And I took this slide from Anil Gupta's paper, and I show you why I use this paper, because he also counted belowides. So there's another intriguing, important phenomenon in the Arabian Sea. That is, of course, the oxygen minimum zone. And that relates to the high productivity, the high organic matter being attacked by the oxygen, leading to a strong oxygen minimum zone. And it characterizes the whole northern Indian Ocean. And so the history of that oxygen minimum zone is also tied to the southwest monsoon, the strength of the southwest monsoon. And so highly interesting phenomenon and unique to the northern Indian Ocean, really. And so I've never seen this somewhere else. And this is what makes the northern Indian Ocean so exciting, is this all deep water that is welling up there, creating high productivity. And then we have an oxygen minimum zone, also very old Red Sea water is flowing out, stabilizing it. And the history of this, it turns out to be perhaps the clue to what's happening. So many folk on board Leg 117 became famous professors. Actually, here's Graham Shamil, here is Peter de Menacle, and many others. Tom Peterson, who sailed on that leg, became very well known. Now, of course, we drilled a world record during that leg at that time, and I think it was 4 kilometers or so of sediments, which was at that time quite something. And nowadays, one would say that's not so much, but during those days, it was a hell of a lot. Very nice people, by the way, all these drillers and cooks and supporting personnel. It's quite funny when I see this again. I immediately recognize the faces, although it's 30 years ago, but I don't remember their names. Now these belowides records. Now, in 1991, I published this record, and you can see this big change around 8 million years or so, 7.5, 8 million years, where we go from low belowides percentages to quite high. And of course, immediately, if you see this 8 million, that's now interesting. In those days, we didn't know about these biogenic blooms in the Pacific and the Atlantic, as I've just shown you. And of course, the timing of it is perfect. It's about 7.5, 8 million years that belowides shoots up. Now, I have to say, I used this 8 million, of course, because that's where the big changes are. But some people would say, oh, there is actually some before that. So you can put the onset of the upwelling systems maybe a bit older if you want to. But I'm coming back to that. So at 8 million years, in this record, we see this increase, and we see this basically foraminiferal blooms at 8 million, of course, correlating with the global biogenic blooms. So what does it mean? Is this now completely monsoonal driven, or is it here a global component? And the answer is, I don't know. Very difficult to say what's really going on here. Probably it's both. Now we look at some counts by someone else in the same hole, and you see a different curve appearing with much lower percentages. And that has confused many people. And here's the third count in this hole. I think it was Anil Gupta who counted this. And we see again a different curve. The reason for that is that these people here used a different size fraction, a larger size fraction. And the percentage belowides in these larger size fractions is much lower than in the smaller size fraction. Now, nobody counts the small size fraction because it's very difficult to count, because the juveniles of other species start to look like the belowides specimens. So most people count in larger size fractions, but the blooms of belowides are actually in the smaller size fraction, as you can see. Now, I don't know how well this was done at the time, but it's much higher percentages than Huang et al. reports in this higher size, in this larger size fraction. But nonetheless, if you look at below it is here, it still sort of records the same 8 million years or so by Anil Gupta. Now, then interestingly, another site on the ridge that I didn't count, but Anil Gupta did, you can see that he actually finds below this all the way back to around 11 million years and 1% or so before that. So if you really want, you could put the onset of the upwelling based on below these around 11. Now, the 1% counts are getting a little bit tricky, really, because what does that mean? There's always some below-these along margins, and you don't need necessarily upwelling to get 1% below-these. And by the way, 1% doesn't mean very much because it's relative. There are other species in there, so you don't know anymore which species is really driving the system. Is it below-these, or is it some other species diluting the below-these record? So be a bit careful with these records and how you interpret them. But if you really, really want, you can put the record back to maybe 11, based on the counts on this site that we didn't count in my days. But however, you can see I did find some below-these earlier on, and some people say that okay, it started somewhere around 13 or so. But I do maintain that the big blooms, the big carbonate blooms, started at 8. Now let's look at some other records, because these are carbonate records. So far we have learned, okay, we have carbonate increase also in the Arabian Sea, most likely, although we didn't look at the carbonate percentages and mass accumulation rates specifically. We didn't do that in those days so accurately like we did later on. But there is something else you can do, and that's geochemical records and some other count records from diatoms and so on, because the biogenic bloom of carbonate may have been preceded by other blooms, let's say based on silica, and that points straight away to nutrient changes. So diatoms need silica, and so it's probably all related to oceanography, nutrient supply, what kind of nutrients and which blooms are we getting in the upwelling cells. Now, if you look here on the left, here we see the coring. We see that the recovery in the deeper part of this borehole wasn't very good. So you have to be a bit careful here. That's why the logs are plotted on the right-hand side to see what's overall going on. But what we have here is an interesting plot by biogenic, who looked at the sedimentology of these sediments. And we see 5 categories, and the left 3 categories are basically chalks with a variability in there. Some have a bit more chalk, more marls in them, and so on, marley chalk, and God knows what names they come up with. But there are 2 facies that are really biogenic facies here are really important. They contain diatoms, and you can see that started around 345 meters or so, and with a sort of summum of diatom production in this interval here. And then, of course, higher up, the diatoms disappeared, and we get the carbonate. Now, the interesting thing then is that this bit here would predict the highest productivity here in this borehole. And you can see that also in the logs. For instance, the uranium log, you can see the highest peak starts here. You can see that uranium is highest since the onset of these diatoms. How old are these? Well, we can see that on this graph here. Gerald Auer and Orr and others, they redid the nanofossil stratigraphy, and they used my old planktic foram levels, and it remarkably lined up beautifully, actually. I'd never thought that that it would work so well when I was so young and did this for the first time. But you can see here some 4M events and some nanofossil events, and it all nicely lines up. And we have here a very good age model. Well, of course, you would like to tune such an orbital, use the orbital cycles to date it all precisely. But as you can see, the recovery at this site wasn't good enough to do so. So here we can actually see the diatoms. The dark browner, these are core photographs, and you can see the gray ones are basically nanofossil chalks. And here's an odd planktic forum here. But when we go to these more brown, dark sediments, you can start to see the diatoms. These red arrows indicate the diatoms, and particularly here in this site, or in this photograph F, you can see beautifully the individual diatoms lying around here. Now, can we call this a diatom bloom? That is something I am still not sure about. When do you call something a real important biogenic bloom? It looks like in F we can see plenty of diatoms, and some of the others not. So the occasional sample will have enough diatoms, I think, to call it a real diatom bloom. And we have to be a diatom specialist, I think, to sort out which species are there and so on, whether they are really representative of a biogenic bloom. But let's assume that's the case. Then that should be reflected in the geochemical records, and he worked hard on the biogenic blooms. As you can see here, we have several geochemical records from 15 to about 8.5 million years. So to the left, we have the carbonate bloom. And what we see here in the top are actually the diatom indicators. That's silica over aluminium. So these are XRF data, and you can see very nicely that the silica started to increase at around 11 million years. These dots have different colors because these samples represent different phases, as I've shown you of the sediments. But you can clearly see an increase in silica at around 11. And of course, if you plot silica over calcium, you see the same. And here's a dust record. That's titanium over iron is plotted here. Interesting. We see that increasing around this time, but that's not what we're talking about now. And here is, interestingly, he plotted manganese over aluminium. And that is important because we see here a very important downgoing trend of the manganese. And that means that the OMZ from about 14.5, 14.6, 14.7 million years started to become stronger. Manganese is an important element that gets affected out of the system if there's no oxygen. And so that's why these numbers are going down if there is an oxygen minimum zone. So it seems that there is a sort of increase in the actually a decrease in oxygen around 14.7 million years, and that's getting stronger and stronger and stronger. And particularly here we can see a very strong OMZ. Now the barium aluminium productivity indicator also shoots up at around 11 million years. Now 11 million years is apparently an important date in the Arabian Sea. And that's not an important date in the Atlantic. So this date seems to be unique to the Arabian Sea. Now, importantly, when we look at counts, for instance, from these samples, then we see a beautiful record here, even clearer, I think, than the geochemical records. We look at the number of diatoms in the sediments, you can see it beautifully shooting up around 11 million years. And that's important, although the first occurrence of these frustules starts a little bit earlier if you want. But the organic carbon shoots up at the same time. It really goes from low values to suddenly above 1%. Now that's important. Together with these diatoms, clearly indicate high productivity during this interval, coming back down at around 9 million years or so. And this diatom bloom seems to coincide with Lewis et al. 2019. So we have a clear biogenic bloom here, but not carbonate. We have now silica. And that's something we did not realize very much on the ship when we were drilling in 30 years ago. And so I think it's amazing that we saw radiolarians and so on, and we realized, oh, there's an Antarctic component there, because there were some Antarctic radiolarians there. But these diatoms clearly indicate high productivity from 11 million years ago, although the OMZ apparently started earlier at around 14.7. I really, by the way, I'll come back to that later, sorry. Here we have the delta 15N of the organic matter, which is important because denitrification is something that is very important in these oxygen minimum zones. And we see a very clear increase happening around 11 as well. So denitrification becomes important. I skipped these two curves. And then most importantly, here we have a sea surface temperature record by Zhuang et al. In 2017. I reviewed this paper and I was absolutely delighted with this. And what you see here is very warm temperatures are being replaced by upwelling temperatures exactly at 11 when the diatoms and everything else is coming in. So 11 million years seems to me, for me now, a very important date. Interestingly, if we look at the manganese depletion, we see that in the site 722, starting at 14.7. You can see indicated here. However, in the Maldives, it started slightly younger at 13. And actually, it was even seen by Jerry Dickens and Owen in 1991 already, I think, or 1994, at ODP site 757 on 90 East Ridge, much further south. So manganese depletion much further south was detected by Jerry, and he was actually, I think, the man behind it, the idea to use manganese. So he should have the glory for this. So, but the interesting point is that we see it in the upwelling site where the OMZ is strongest, earliest, of course, before the OMZ all the way reached out to other places in the Indian Ocean, and it really came far down south, actually. Quite astonishing. So that's what we see here. Here we have the Indian Ocean. Here we have the OMZ, oxygen minimum zone. Very strong OMZ here. And during time, at its zenith, it even reached this site here at the 90 East Ridge. So the OMZ was stretching out all the way down south when the upwelling and productivity systems must have been really turned on at 11 million years, starting at 11, and let me see, hang on, I have to go back. And then around 11, yeah, Dickens and Owen, and then further south detected at 11 million years. So again, 11 million years, very, very important. And at 11 million years, not much is happening in the Atlantic. So that's typical for the Northern Indian Ocean. So when we start to put it all together, it becomes a very complicated story, actually. And I think Or did a very good job here, but it's not complete, really. But it doesn't matter. It shows the picture. Here we have time, 15 million years to 9. And here we have his upwelling OMZ sort of signature. And he says it was strongest, slightly starting earlier than 11, and then waned down back down. And we can see around 9 it became less intense. How does he interpret it? How can we interpret it? Well, what we see here at 40.7, we see the first signal of OMZ, manganese depletion on the above the Owen Ridge. Now, interestingly, we say that that's possibly the onset, but to be honest, we don't have an early Miocene record of these places. So maybe it started earlier, or there maybe were already attempts to sort of make these OMZ zones strong in the early Miocene, but we simply don't have a record there. And so we just pretend that that's correct. This is sort of the onset of that. And then what we see here, he plots this here, a cooling from 14. And I sort of disagree with that actually, because the cooling started at 11, that we, for the first time, really upwelling temperatures. And Lord behold, at that point, we get silica accumulation and denitrification in the Arabian Sea. So 11 million years for me is standing out. Why? Because it's unique to the Arabian Sea, but how unique it really is, we don't know, because maybe there are already sites in the Pacific that show similar silica blooms. I had no time to go through the literature for that, but I suspect there may be, but certainly not in the South Atlantic. So it seems to me that 11 million years is a really important date in the Arabian Sea. And then, of course, when we go up, we can see that the carbonate blooms at 8 million years start to take over. In other words, there is something going on. And we can't really put our finger on it now, because in fact, probably we are looking at upwelling all the way through productivity, like you see in the modern upwelling systems, which in the core of the systems, we see these diatom blooms. And why they disappeared is probably related to a switch in nutrient supply. And it may relate to Antarctica. Let me try to explain. What we see here at 40 million years is of course right happening after ice growth on Antarctica, and other people here we see the Indian observations in the Indian Ocean. Other people have seen silica accumulation starting around 14, and I'm talking Keller and Barron a long time ago. So it seems that we get silica supply from the south somehow, and that may relate to intermediate waters or deep waters coming from the Southern Ocean. And interestingly, other people observe similar things. For instance, Smart et al. In 2007 actually saw already or postulated that we have Antarctic intermediate waters in the Indian Ocean. That's important because he spotted it based on benthic forams, I think, and also Anil Gupta did something like that. But it's right prior to the biogenic silica deposition. So it seems that what's happening in Antarctica and the whole ocean rock field system, that actually can be connected to these blooms in the northern Indian Ocean. Now, that is important because it shows that global links are controlling the bloom systems in these upwelling cells. Now, but this upwelling cell here is clearly, these upwelling cells here are clearly unique to the northern Indian Ocean. So I would say, we can safely say that the modern sort of upwelling system must have started at 11 and maybe already kicked in a bit earlier. But here what we see is the OMZ depletion at 14, clearly related to what's happening in the rest of the Indian Ocean, and probably related to what's happening around Antarctica. So we have expansion of the ice sheets and we have a reorganization of deep water in the Indian Ocean. Now then we see here the carbonate crash indicated here, and then followed by the carbonate blooms at 8 million or plots here, this interesting turnover in the nanofossils, but you could have plotted the below this curves as well, or refer to it. It doesn't matter. So it's all about Antarctica freezing in, causing changes in the atmospheric system, causing changes in the deep sea and in the intermediate waters. And we can see the consequences in other places in the Indian Ocean. For instance, Groeneveld et al. From 2017 related beautifully what's happening offshore Australia to what's happening in Antarctica. So what I'm trying to say is that we have the Northern Indian Ocean, unique with its oxygen minimum zone, unique because of its upwelling. And we see clearly events happening that relate to global climate. Now, can't we then say anything about when that modern upwelling system started? I think we can, because this 11 million year evidence now here is so clear in Northern Indian Ocean, although it may relate to the nutrient supply from down south. But nonetheless, if we have supply of nutrients from down south, we still have to have the southwest monsoon winds to bring it up to the surface to create these biogenic blooms. So for me, the modern upwelling system clearly was there around 11 and possibly started somewhat earlier, but that's less clear. Simply, we don't have enough records at orbital level to precisely date it all. So my recommendation would be to go back and drill far more holes in that Northern Indian Ocean, offshore India, of course, and other places to really quantify it. The problem with LEC 117 was lovely records, but when we drilled deep, then the recovery wasn't so good, and we were not so good at all this tuning in the Miocene, and so we need now complete records of the Miocene to confirm these changes in other places in the Arabian Sea and so on. And of course, Anne Holborn has done similar things offshore further to the east, and so I'm sure, but I'm not taking her thunder, and she will show that herself. But again, you will see that these ages that we see here will be coming back. So my conclusion is, very complicated system. It's not very easy to put your finger on when the modern upwelling system started. 30 years ago, it was easy. We just simply said, come below it is, and that's it. And that's what I did, and came up with 8 million. It's not necessarily wrong. It's just that it was a bit simple. There were not other proxy records to look at that, or we didn't have people to do so. But now, in the last decades, these modern proxies were coming through, and using them, we can see much more, and we can see that maybe something happened already at 14.7, the OMZ, but even that can be a little bit hazardous to say because we don't have records before that time. But let's assume that's the case, then we see this clear intensification at around 11 or slightly earlier. And then nutrient supply created these blooms. Southwest monsoon winds must have been there, otherwise you don't bring up the nutrients, so we need upwelling. And then we have a nutrient shift, and somehow we lose the silica and we switch to a carbonate system at around 7.5, 8 million years, and that was the below this record I was recording. So much more complicated than we thought at the time. But boy, it's so interesting, and I hope you have enjoyed some of this, and hope I have clarified a little bit about these below these curves, but that's just one part of the whole system, and we must look much wider, and the whole thing becomes much more interesting. Thank you very much.
Great. Thank you. I will let. Oh no, I was having a bit of a connection issue there, getting back online for a moment. But here we can let everybody curate their questions here for a moment. We have already one at least. Excellent, excellent. So the first question here is from Boris. So Boris, would you like to ask your question, or would you like me to read it out for you?
Yeah, I can ask it maybe.
Okay, great.
Thank you very much. It was very interesting. I first have to say that. I was wondering that since you see that the upwelling in the Indian Ocean intensifying in a sense through the silica record, the diatom records, and since the Indian Ocean upwelling is seasonal, would this probably mean the strengthening of seasonal winds and land-ocean pressure gradients at that time? So also monsoonal intensification. Do we have any clues about that?
Yeah, very good. Yeah, so it's all related to winds, of course, and not rainfall. I mean, there's an interesting problem. We talk monsoon, we actually should really part of them we really try to identify. And in this case, it's winds, obviously, as you say, is the southwest monsoon. And the whole idea is, as you say, there's the temperature gradients between low and high latitude. So because of the cooling in of Antarctica, and it goes in stepwise, you know, in 3 steps or so. I mean, Anne Holborn's records are beautiful. Delta 18O records, you can see 3 very clear steps, and it's getting colder and colder and colder. And of course, that changes the temperature gradient between the low and high latitudes. And of course, the winds speed up because of that. The fronts move northwards. And so the jet system becomes stronger. So this is the whole idea that this stronger jet system then creates the upwelling, strong upwelling, and so, but at the same time, you know, you get nutrient supply from the south as well. So old water from Antarctica, rich in nutrients, maybe suddenly arriving in the Arabian Sea, together with the strong winds creating the upwelling, creating these biogenic blooms. So I think you're right, Boris. It's the temperature gradient.
Thank you. And I think I have the other question too. So, and actually it's linked. So is this maybe why we see in many cases obliquity controlling sedimentation rates, such as in Drury's record, but we see that in the earlier part, so after 8 million years old, in the calcium carbonate sedimentation rates. And I was wondering, what is the mechanism that through which obliquity controls calcium carbonate sedimentation rates in the Atlantic, South Atlantic?
So yeah, that's an interesting point. And obliquity means high latitudes, really. And so I think Anne has written all about this, and she sees it in her records as well, further to the east, and also in other records, as you say, it has been seen. So this 8 million years is not simple, and it's not a simple biogenic bloom in the Arabian Sea. It's global, and but that relates to what's happening in the high latitude somehow, and it's ice built up, and some people believe that the northern hemisphere ice started to expand there. We know that temperatures drop heavily in the Mediterranean, but also in other places in the Pacific. So most likely there was already some ice in the northern hemisphere as well. It means for me that this is global, and it relates to ice built up, probably in the northern hemisphere. Now, how that then creates more these carbonate blooms, I don't know. But maybe it hasn't had an influence on the weathering rates, why there are more nutrients going into the sea, and not so favorable for silica blooms, but maybe for carbonate blooms. So maybe a combination of global climate change, more tilt-driven, and maybe triggering something like weathering changes, and maybe then a nutrient change in the ocean. So or the Antarctic intermediate waters were getting less important somehow, or Antarctic deep waters. But you know, all these questions we have, of course, as a group of paleoceanographers, and it's very difficult sometimes to put your finger on it. I hope this helps a little bit.
Good, thank you very much.
Okay, I think we have a comment rather than a question from AD Singh in the chat. Would you like to comment on that, or I'll read it out? Okay. So.
Hi.
Okay.
Hello. Hi, Dick.
Yeah.
So I think, yes. So we have recorded the fossil group, you know, from the DSDP sites 219, 219 and 237, and of course, you know, at the DSDP site 214 also. That what we have seen a typical warm water farms, that is the fossil group, has disappeared at around 11 million years. So I mean, that shows, that reflects that there has been a major change in the paleoceanographic event, you know, at around 11 million years. That's what you say. So I think this this observation, it very well agrees with you that something has happened at around 11 million years.
Oh, that's a very welcome comment. I think that's you know, Jim Wright has thought a lot about what's happening in the Indian Ocean. You know, that every time we get one of these events, that we get a sort of new deep planktonic fauna developing in the thermocline that relates to development of the intermediate waters also. So maybe that's the answer to your question. So, but it's very interesting that you say that this important event, which it is around 11 million years. I'd never thought of that. Thanks very much for alerting me. Maybe we can email about it, because it's
right.
It really add to this 11 million year event.
Right. Okay.
Okay. Well, I don't see any more questions in the chat. And then let me check YouTube here for a moment. There aren't any questions left over in the YouTube. So does anybody else have any questions or not? I think, oh, here we go. We've got a couple more questions that just came in. We have one from Nagender Nath. I don't know if you are able to read out your question, or if you'd like me to read it out for you. Give them a moment to respond. Okay, so what they ask here from Groa is, they ask, how well do these upwelling records compare with regional, or sorry, with erosional records in the eastern part of the northern Indian Ocean?
Very interesting question. And hi, Nagender, how are you? I hope you're well. We sailed together on one of 907 Maldives. Anyway, yeah, so they sort of link up. And the reason is that some of these events are global, like the 14 million year event, let's say 13.9, 14 million years, and the 8 million years. So these weathering records, in that sense, should start to line up, but with these two events, because these global changes must have influenced the weathering rates. So, but weathering is a complicated business. It's climate driven, it's tectonically driven, and so Peter Cliff knows everything about that. So he really is the guy to answer it. But I'm sure, I think there was a paper by Peter at some point who said that there was I think a drop in weathering rate at 14 million years. So it sort of follows the climate curve, the weathering rates, and so they're totally different from upwelling. But these two events, like 14 and 8, you bet that there will be a correlation to what's happening in the weathering world. But I don't know about 11 million years.
Okay, and we have another question also in the chat that's also talking about the responses of some coral reef systems. So Maryline, would you like to read out your question, or would you like me to read it out for you?
Yes, I can read it. Yes, I was, hello, Dick, very interesting. I wanted to know if at 11, if there were some major change in coral reef biology around the Andean, maybe because you need this carbonate to come from somewhere, maybe eroded from shelf. If the sea level had dropped already quite a lot, maybe then that would fuel the production of carbonate in the open ocean.
That's an interesting question. Where is all this carbonate coming from? I personally, yes, at 8 million, or you mean at 8 million, I presume?
Maybe at 8 million as the main event, but maybe starting a little bit before. And because this will imply a change in sea level, you may also explain why it was actually going relatively slowly,
Yeah, that's an interesting thought, because if you drop the sea level, you expose the shelves, and previous carbonate build-ups will be eroded off and their products into the sea, and then you expect a CCD drop, I presume. So yeah, I sailed on the Maldives leg, and Christian Bessel is the one who can answer this much better probably. But when we drilled there, we observed that during the 14 million years, we get a totally different system there in the Maldives, where we get suddenly this inner sea sort of sediment drift developing, and it's actually at 13 plus or minus 500,000 or so. But so the carbonate platforms were responding. Of course they were responding, and it's a global event, and sea level drops, much colder, and so many platforms started to of course to dwindle and to wane. But I really would like to leave this question to Christian, because he will give a lecture in a few weeks' time, and he may be much better positioned to answer your question.
Okay, thank you.
Excellent. So I think that we've probably run out about time now. We've had you answer enough questions for us, and we've had an excellent lecture by you. So I just have this opportunity to thank you very much again for getting up so early and sharing a lot of your research with us. And so with that, I just want to remind everybody that next week on the 7th of April, we will have Anne Holborn talking a little bit about their research. And so you've been kind of nicely leading into their research a little bit today with some of your comments. And then the next schedule will be again in 2 weeks on the 14th of April. So again, this exact same time. Just for most of us anyway, with Tomo Arino as well. So again, stay tuned, check out the announcements from us hosts, and then thank you very much again, Dick, for this excellent presentation that will give us some food for thought. Yeah.
I can highly recommend Anne's talk, because he has these beautiful records, or IODP records. and orbitally tuned in the Miocene zone. So rather much more detailed than the site 722. But nonetheless, I hope to have introduced you to a lot of problems and interesting thoughts. That's all.
Excellent, excellent. Well, thank you again. And again, good morning, afternoon, and evening for everybody. And I hope you enjoy the rest of your days.
Bye-bye.
Bye.